The goal of this video is to look at goal 8, which is how to perform a two-proportion z-test for the difference between proportions. In the last video, we talked about two-proportion z-interval. In the two-proportion z-interval, basically what you did was you took two samples and found the difference between them. You then use the difference in the sample to try to infer what the true difference in the population may be. So even though your sample has a difference, it doesn't mean the population has the same difference, but the population difference is hopefully nearby. That was the idea in the other video of the two-proportion z-interval. The two-proportion z-test is similar in the fact that it uses two proportions. So you're still getting two sample proportions, and you're still going to look at the difference between them, how different one group is from another. But the difference in the test from the interval is that the test is just trying to see if the population is truly different. So even though your samples come out different, it's possible the two populations aren't different. So what you're trying to do is, from your two samples, see if the actual population has a difference or not. Now, the two scenarios are your initial populations don't actually have a difference. If that's the case, the reason you're seeing a difference in your samples is just natural variation. Even if the two populations have the same value, same proportion, you may be seeing a difference in the proportions just from natural variation. The other possibility is the two populations are actually different. And if the two populations are actually different, the samples, of course, would seemingly come out different as well. So it's possible the reason you're seeing that sample difference is because the population's different. So the test is going to tell us from the difference in our samples, do we believe there's an actual difference in the two populations? That's the general idea. Let's look at some concrete examples to help you hopefully get an idea of that. So we're going to do a hypothesis test with two proportions. This first example, I can't fully do out an answer because we don't have information about the sample sizes, but it's just a good thinking exercise. So the major question that we answer with a hypothesis test with two proportions is what's on the screen is there a significant difference between the actual population proportions? So just a really simple example, a poll is given. We'll say it's the governor. We'll say it's our governor, Governor Cuomo. So Governor Cuomo initiates a poll, and in that poll, 58% of women approve of the job he's doing, and 63% of men approve of the job he's doing. The question for Cuomo is, do men and women in the population actually have a differing opinion of him? Now, the sample comes out with a 5% difference. It looks from the samples that men approve of him at a 5% higher rate than women. But the question that we want to answer is this indicative of men actually liking women at a higher, or men actually liking Cuomo at a higher rate than women? So the two possibilities here are men and women actually like Cuomo at the same rate, that there's really no difference between them. The only reason we see men higher than women in the sample is through natural variation, that we happen to get a sample that was a little more men and a little less in women. The alternative is that men actually do have a differing opinion of the governor than women do, that maybe men do like him at a higher rate. So it's possible the reason we're getting the 5% difference is because men in the population actually like him at a higher rate. So that's why the samples are coming out with that difference. Now, the problem is in this example, without any sample information, it's hard to tell if that 5% difference is significant or not. So basically, if we assume men and women are the same, is that 5% difference likely to see, or is it not likely to see? Now, in this example, I can't determine that because I have no other information. But I just put this up as sort of a thinking example to be able to show an example in concrete terms of what I was just talking about on the goal screen. In order to show a full out example. I picked another one. This was in the textbook. It was a study about snoring. So this has enough information for us to actually answer the question, unlike this one, where we just see a sample difference and we're not sure about the population difference. All right, so this is a full example, and I'll show all of the steps. So this is what I'm going to use to do the full hypothesis test. Now, the hypothesis test of this type still has the same steps like the one we did for one proportion. So the four major steps are: we're going to show the hypotheses, we're going to show the conditions. Once the conditions are met, we're going to do the calculations to see how unusual our sample is and get a p-value, and then the p-value will let me make a conclusion about the null hypothesis, whether we'll reject it or fail to reject it. So the big four steps are the same in every test. What I'm going to do is use this example to illustrate what are the differences from what we did before. So going forward, we're going to do more intervals and more tests. Most of the time, what I'll try to do is compare and contrast them. They're the same in structure. I'll go over the major differences. So this example here, it's been up on the screen for a while, is about snoring. This was actually a real study from what I gathered out of the textbook, so that's why I'm using this. I made up the one about the governor. So the snoring study observed 995 people, and it basically split those people up into two categories, under 30 and over 30. So when they were split up, of those 995, 184 people were under 30, and 811 of them were over 30. Of the under 30 category, 26% of them snored. Of the over 30 category, 39% of them snored. Now, what we're wondering is this sample difference is 13%. There's a 13% difference between those over 30 and those under 30. We want to know, is this difference significant in the fact that the population has a difference in snoring? So one possibility is people under 30 and people over 30 snore at the same rate. And we only got this 13% difference due to natural variation. The alternative idea is maybe the reason we're getting this 13% difference is because there actually is a true population difference in those over 30 and those under 30. So the hypothesis test is what we use to figure this out. So does this sample support that older people snore at a different rate than younger people, or is this possible that they come from the same rate and natural variations what's causing that 13% difference? All right. Let's use this to go over the steps and what's different. So at the top here, I put the test structure is similar to a one proportion test. Once again, I already went over that the hypotheses are something we're going to state, the conditions, we're going to use a normal curve in order to test how unusual something is. We'll get a p-value, and then we'll make a conclusion at the end. So that structure is the same. Following are the differences. So the first difference is in how we make our hypothesis. So the hypothesis for a one proportion test involved our null hypothesis being the normal state of affairs, and then the alternative was a change from that normal state of affairs. In a two proportion test, the normal state of affairs is always, or the assumption I should say, is always that there is no difference between the proportions. So we will always assume when we do a two proportion test that the actual population groups have no difference. So if it were the Cuomo example, it would be that men and women actually have no differing opinion of him, that they like him at the same rate. That would be our assumption. Now, we didn't have enough to do that example, so using our snoring example, the null hypothesis would be that both the old people and young people snore at the same rate. Now, the way we write that is if we subtracted the two population proportions, we would actually get 0, meaning they were no different. Now, P1 and P2 can be whichever, but I normally make P1 the larger number That way you subtract the smaller number from the larger number and you get a positive difference. If you swap them again, negative difference, it would still work. It's just easier to think about a positive difference. So I'm going to have, for our example, this P1 is going to be the older people because they snort at a 39% rate, and or for their sample, and the younger people snort at that 26% rate. But our assumption is going to be that even though our samples came out differently, that the actual population has no difference. So our assumption is the population number for old people minus the population number for young people, their snoring rates are actually no different. They're zero when you subtract them. If I'm thinking that there is a difference in the groups, that would be my alternative hypothesis. So my alternative would be that P1 minus P2 would not be zero, meaning that it would be some positive or negative difference. Now, you can do a one-sided or two-sided test on this. So if you do a two-sided test, which this calls for, because they're just asking, are the two numbers different or are they the same? If they're just in general different, we're going to look at both sides. We're going to just put it's not equal because we'll care about whether it increased or decreased. It's possible to do one-sided tests. If I just wanted to know are old people snoring at a higher rate, I would use a greater than here. Or if I was wondering if they were snoring at a lesser rate, which wouldn't make sense in this problem, but you could use a less than side. So realize that this could be a one-sided test with a greater than or less than. In this case, I'm doing the not equal to because it's a two-sided test. I care if the young people and the old people are different in general, not if they're one's greater than the other. So if they're different in general, that's my alternative. So the null hypothesis is that there is no difference in the population numbers. Young and old people snore at the same rate. If that's not true, my alternative is that there's some meaningful difference, that when I take the difference between old and young people, I get something that's not zero, meaning that their rates are different. So this is the first major difference when you do the test. When we go to do our normal curve, when we get to step 3, we always need a mean and a standard error. The mean, in this case, what's the middle of our normal curve, is always going to be our null hypothesis. The assumed mean difference is 0. That's what it always is. We always assume that the difference in the population is nothing. So since the assumed mean difference is 0, that's always going to be the center of our normal curve. So whenever you do a two-proportion test, the center of your normal curve is 0. What we're going to put on the normal curve to test how unusual it is our sample difference. Our sample difference is p hat 1 minus p hat 2. In our problem for the snoring, it's 13%. In that Cuomo example, it was 5%. So what we're going to do for the snoring example is we're going to assume the population has no difference and then see how likely it is that we got the sample difference that we did. How likely is it that we get a 13% difference if the population has no true difference? If that's likely to get 13%, then we say that there probably is no difference in population. If it's very unlikely to get 13%, we go, well, it's probably true that the populations are actually different then. That's why we're seeing the 13%. So the mean of our curve is always the null hypothesis, which is 0 for this kind of test. That's different from before. In order to test how unusual our sample difference is versus our hypothesized difference, we need a measure of standard error. So this standard error formula is actually the same that we did in the last video, which involved doing a two-proportion interval. Now, there's a problem with this formula. There's always got to be a problem with something. This is the standard error formula for two proportions. There's one problem with this in that when you do the confidence interval, you use proportion 1 and proportion 2, and they're different proportions because they're your hat values. The problem with this is as follows. In our null hypothesis, we assumed that the two population numbers weren't actually different. So logically, there's a problem with assuming that P1 and P2 are the same, and then going to this formula and putting in a P1 that's different from the P2. Our assumption is that P1 and P2 aren't any different. Remember, if we go up here, that's what this means. We're assuming P1 and P2, when we subtract them, they have no actual difference, meaning they're the same number. So we actually can't use this formula as is. It needs a slight modification. So this is what makes this test a little trickier, is when we go to calculate the standard error, we have to come up with a p-hat value that's not different based on the different groups, but we need one that's the same for the entire group. This is called pooling. So we have to come up with something called the pooled number, which is referred to symbolically as p-hat pooled. So the logic here is that according to the null hypothesis, P1's the same as P2. So we need an estimate for P1 and P2, which is the same. Our samples came out different, but we want to know what is a reasonable number. If they were the same, what would they be? So to do this, to get that estimate, we combine the results under the assumption that they truly have the same proportion. So we're going to assume, like we did in the null hypothesis, that the young and old people have the same proportion. To do this, we need to do something called pooling, which is to come up with a new number. Basically, what the pooled number is what would the snoring rate be for everybody if they were all put together? Because we have a snoring sample rate for the young and a snoring sample rate for the old. Say we didn't separate them into old and young, what would that general number be put together? That's the number we'll use for p-hat. That way we're not putting in two different numbers, we're putting in the same number. So this is a little tricky, but when I show it to you, it just requires an extra calculation. So you have to remember when you're doing this two proportion test that in order to use the standard error formula, we're going to need to calculate this p-hat pooled number. So when doing the interval, we can put in the separate numbers, but when doing the test, I'm going to give you the modified formula for this. All right, so we're going to do this thing called pooling. How do we pool? We use this formula that's below. So to pool the results, we basically want the success rate of each group combined. We want the success rate for the whole group. So now success in this case is getting someone who snores. If I was doing the Governor Cuomo example, we would basically want how many people like Governor Cuomo in general, not broken up by male and female, but just generally how many people like him. For this example that I'm actually calculating, we want what's the general snore rate. So that's what the p-hat pooled value is. How do you get it? Well, you take the success rate of the first group and add it to the success rate of the second group. Basically, the number of people who snore who are young plus the number of people who snore who are old. That gives me the total number of snorers. I then divide that by the total number of people. So N1's the young people, N2's the old people, their totals. Basically, all this formula does is add up all the people who snore, all my successes, and add up all the people total and divide the two. So it's really not that difficult to do, but you have to know to come up with this. So to get the p-hat pooled number, for this particular example, I need to figure out how many people are snoring and in each group, and then figure out how many people there are in each group. Now, if we go back, let's go forward because I think all right. So to actually answer the question, the problem is I don't have the number of people. I just have the percent. So if you don't have the number of successes, you'll have to figure it out. To figure it out, I'm going to take 26%, 0.26, and multiply it by 184. That will give me the number of people under 30 who snore. Now, keep in mind, these numbers are usually a little bit rounded. So when I multiply 0.26 by 184, I actually get a number that's a little bigger than 48. I'm going to round that down to 48 because somebody probably rounded this off to begin with. So there was probably 48 people and this just got rounded. So if it's a little off, round it to the nearest person because you can't have a fraction of a person snoring. So to get the success rates, 26% of the 184 people under 30 snored. That means there's 48 snorers. 39% of the 811 snored. who are older people. That came out to be a little less than 316, so I rounded it up to 316. So to get the pooled number, which I'll show on the board afterwards, to get the pooled number, I'm going to take the number of people who snored, who are young, 48, add it to the number of people who snored, who are old, 316, and add them together. I have a total number of snorers, that's 364. Now, these n numbers are the total number of people. The total number of people are 184 under 30 and 811 over 30. That's what goes here. So in the bottom, I'm going to have a total of 184 young people, a total of 811 young people, for a total of 995. So my p hat pooled is going to be the overall rate of snorers, 364 out of 995, which comes out to be approximately 36.6%. So I just talked about how to get the success numbers. Sometimes they give them to you. If they don't, use the percentage to get them. Now, once I get this p hat pooled number, this formula that I showed, if I can get this to display it, in the standard error, since I assume these were the same, I'm actually going to plug in the pooled number for all of these. I'm going to plug in the p hat pooled for both and the q hat pooled for both. There it is. So this is the standard error that you use. So if you're going to do this test, the way you calculate the standard error is to plug in the pooled number everywhere. So the p hat pooled is 0.366, and I'll show that on the board in a moment. But that's what I calculated out to be. So I'm going to put 0.366 here and 0.366 here. Now, if I subtract from 1, I'll get the q hat pooled. So if I subtract from 1, I believe that's 0.634. I'm going to put 0.634 here and 0.634 here. Now, I still use the individual numbers. I still have 184 and 811 for my totals. But notice I'm not using the success rate of the young people and the success rate of the old people. I'm using the pooled number. So the pooled number is assuming that both groups are the same. So I'm using the both groups pooled number. That's the overall success rate. So that gets around the problem that we're assuming the proportions are the same. Instead of plugging in different proportions of the formula when we assume they were the same, that doesn't logically make sense. This gets around it. So basically, we're assuming the population's the same. We came up with a p hat and q hat that assumes that basically that 0.366 is the overall rate, and use the overall rate in this formula. All right. With that in mind, now I can show you the entire process of doing the test. So those are the big differences. Once we've done all this, I'm going to do like we always did, find a z-score, find a p-value, then make a conclusion. All right? So hopefully you understand all that, and now we're ready to answer this question. So I want to see, is this 13% difference actually meaningful? So is it 13% different because the actual populations are different, or is it 13% different because natural variation, that really they snore at the same rate, and I'm just getting some variation in my samples because that happens? All right, so on the board, I have the full procedure. All right, so I will explain each part. I talked through the p hat pooled calculation. It's up at the top of the board. So before you do this, you want to get that pooled number. If you're going to run a two proportion test, you need to get the p hat pooled. So the way I found it was I found the number of snorers amongst the young. That's the top left, 0.26 times 184. I found 48. I then found the number of old snorers, 0.39 times 811 was 316. And then the way I calculate the pooled numbers, I took the total number of snorers of each group, added them, got 364. Took the total number of people, got 995. So the general rate of snoring, assuming that there's no difference between the old and the young, the snore rate for everybody is 0.366 or 36.6%. So I'm going to use that later. So now I start running the test. So step one of the test is always to make the hypotheses. That was one of the differences I showed you. So my two hypotheses are there. The null hypothesis is P sub A minus P sub Y equals 0. Now, I mentioned that I'm going to put the one with the higher rate first. So P sub A, I use A for aged because I didn't want the P sub O for old would have looked too much like the H sub O. So I used P sub A, it just means aged, and Y means young. So P sub A is the old people rate of snoring in the population. P sub Y is the young person rate. Remember, my null hypothesis is that if I subtract those two rates, I get 0, meaning they're the same. Now, you can just put the left part. I did put what it means in English. So the null hypothesis is just saying that those over and under 30 have the same snore rate. That's my null hypothesis, my normal state of affairs. If I don't think that that's true, then I would go with the alternative. The alternative is that if I subtract the two of them, I get something that's not 0. Now, since I just wanted to see if there was a difference, once again, this is a two-sided test. It's possible that could be a greater than or less than in different problems. But in this particular problem, I just want to see our young people different from old people. And if that's the case, when I subtract them, I won't get 0. So I put in English what that means. The symbols mean, in the context of this problem, that those over 30 and those under 30 have differing snore rates in the population. All right, so that's my null and alternative hypothesis. Then I have to check the conditions. The condition check is the same as for the two proportion interval. The first condition I have to check is independence. Well, one person snoring shouldn't affect another's. That would make sense if you're randomly picking people specially. And nor should one age group affect the other. So remember, you have to check within the groups and across the groups. An old person snoring shouldn't affect a young person snoring. Unless they were related or something. Once again, you're randomly picking, so that's unlikely. Basically, one person's snoring should affect another, and one person from one group shouldn't affect the other group. So that's reasonable to believe that condition's met. The randomness condition, if this were an AP problem, they would probably go out of their way to tell you that it was randomly done or tell you who did it. I'm trying to make the examples not 5 paragraphs long like in the AP problems. So I'm just putting them, I'm going to trust the people doing this study. All right. The 10% condition. Once again, it doesn't say who the population is. In an AP problem, they would be a little more specific. I'll just say this is a typical study maybe of the nation or maybe even in New York State. Basically, 184 people under 30 isn't going to be more than 10% of any significant population. And 811 of people over 30 isn't more than 10% of any population. So especially if we were doing a national study, these are way under 10% of the population. So we can assume that that's met. The last part's to do the success-fail condition. Now, the success-fail condition is do n times p and n times q for both groups. I'm using the pooled number because, once again, my assumption, so this is one of the first times I'm using the pooled number. I'm using the pooled number because my assumption is that the populations are no different. So I would expect n times p hat pooled and n times q hat pooled for each group. So the first group I did were the old people. I did n sub a times p hat pooled and n sub a times q hat pooled. So I expect 297 people of old people to be snorers and 514 not. And then of young people, I do the same thing. I expect 67 of them to be snorers and 117 not. Now, that's a little different than my sample numbers, but that's because my sample numbers are what actually happened. This p-hat pool is assuming that everyone's under the same rate. The important thing is that all 4 of those numbers are greater than or equal to 10. So for the success-fail condition, you don't want anything under 10. They're all way bigger than 10. So all the conditions are met. Now, the only thing I didn't have room to write is usually when you're done with the conditions, what you state is, because the conditions are met, I will perform a 2-proportion z-test. Now, I didn't have room to write that on the bottom, so make sure that on an AP exam, you need to state what procedure you're using. Because I'm testing the difference of 2 proportions, you would just say when you're done with the conditions, because the conditions are met, I'm going to perform a 2-proportion z-test. All right? Since the conditions are met, that means the sampling distribution is normal, and it means I can use a normal curve. So the next part shows how do I use the normal curve to test if this is if the sample is indicative of a significant difference in the population. So here's part 3, which is the mechanics, and then part 4, the conclusion. The way you set up the normal curve is the mean of the normal curve is your assumed mean difference, or what you've said in your null hypothesis, which is 0. So the good news about this procedure is that the center of the normal curve is always 0. It's always what we hypothesized. So we're assuming that there's no difference in the population. So most of the time, the difference of the population would be around 0. Now, what we're trying to test is we got a difference of 13. If the differences come out as 0, how likely is it that my difference is actually 13? So from a population with no difference, how likely am I to get a sample difference of 13? Well, we're going to test that. I have my null hypothesis is 0. What I'm testing is that 13%. So I showed that p hat, my actual sample values, p hat A minus p hat Y was 13. So I'm assuming there's no difference. I want to see how likely it is to get a 13% difference. And that's what's over here, and that's what's on the curve. Now, the only way to know how far out 13 is I need standard error. The standard error is that formula I gave you at the end. So you need to use the standard error pooled. So you have to use these pooled numbers instead of the p hat A and p hat Y numbers. So notice I used p hat pooled and q hat pooled in both slots. I still retained the N1 and N2 numbers. So I did use 184 for the number of young people, 811 for the number of old people, but I used the pooled numbers for the P1 and the P hat 1, P hat 2, P hat 1, Q hat 1, P hat 2, Q hat 2. So instead of plugging the different numbers, I just plugged the pooled number in everywhere according to that formula. When I did that, I threw that all in the calculator, and my standard error is 0.0393. So it's important to use the pool number, or else you don't get the right number over there. Once I have the mean, the number I'm going to test, and the standard error, well, I just come up with a z-score, and then I come up with a p-value. So the z-score formula is the value I found minus the mean over the standard error. I get 3.307. Now, if you've been paying attention in class, you know that that's kind of a rare result. To get something that far out is unlikely. But I want to know, I need a measure of how unlikely. So I need to measure in the calculator, if I'm at 3.307 standard deviations, how much area is it from there or more unusual than that? So the area of this is calculated over here with the normal CDF. I did normal CDF in the calculator from 3.307 to 999, and I get a very low number. I get 0.000472. Now, because this is a two-sided test, that one's not my p-value, that one there, because that's only the one side. So the area of this one side is the 0.000472. I need to double it because I was looking for whether it was unusually high or unusually low. So my actual p-value is double that number I just got. I kept it more precise in the calculator, so doubling what I got in the calculator, I got 0.000943. So that's a very low p-value. Basically, what that tells me is that if the true population difference was 0, how likely am I to get a 13% difference in my samples? It's not very likely at all. It's less than a 1 in 1,000 chance. So remember what that means is, since it's so unlikely to get that, I tend to think that instead of the null hypothesis being the case, it's so unlikely that this would happen under the null hypothesis, it's probably the case that this null hypothesis isn't true. So once I have the low p-value, I can now make my decision. 4 is my conclusion. So remember that you have to decide whether you're going to reject or not reject. So I put, due to low p-value, I'm going to reject the null hypothesis. And then after that, make sure you put it in context. So what does it mean to reject a null hypothesis? Well, that's what it says after it. It means that it is reasonable to believe that those under 30 snore at a different rate from those over 30. So this is the full-out test. The sample difference seems like it was significantly different because the populations were different. It's very unlikely the population was the same and I got this level of difference. All right. So our major conclusion here is that the p-value is low. I'm rejecting the null. And if I reject the null, I go with the alternative. The alternative was that those over 30 and those under 30 snore at a different rate. So this is a full out two proportion test. The major differences from the one proportion test are the null hypothesis being the 2 subtract to be 0, and the need to calculate that p hat pooled and q hat pooled. We are using basically the same formula that we did with the confidence interval, but instead we have to put in that pooled number. Once again, the logic of that is because since we assumed the proportions were the same, the pooled proportion has to be used because that's assuming that they come from the same group and not assuming that they're different. Our sample was different, but we're not going to use those differences in the formula. So make sure that you find the pooled numbers and use them in your standard error formula. On the AP exam, they do give the formula with the P1 or P hat 1, Q hat 1, P hat 2, Q hat 2. They also do give a formula for how to pool, but they don't tell you how to use it. They don't give you this formula and go, oh, by the way, plug in the pooled version when you do the test. So you have to know that. But it's essential that you do that because if you don't do that, you get the wrong standard error and you can get the problem wrong. All right. Also keep in mind that this was a two-sided test. It's possible that they could ask for a one-sided test. The way it would have been different had they wanted a one-sided test is they would have asked, instead of, oh, the snore rate's different, they might have asked, oh, are the snore rates of young people lower than that of older people. Even if we didn't do a two-sided test, we still would have rejected the null. If it was a one-sided test, we would have gotten this number, and it would have rejected the null as well. So either way, we have reason to believe that there's a significant difference. And the fact that the p-value is very low gives me more confidence that we made the right decision. Because like I said, these tests can be wrong. There are errors associated with them. But this is the best we can do. It's better than nothing. So this procedure is likely to be right most of the time. And due to this very low p-value, it's pretty reasonable to believe that that the null is wrong. Either that or I somehow got this 13% sample and it almost never happens. I did something that's has a less than 1 in 1,000 chance of happening, which is extremely unlikely. All right. I'm going to give you one to try. I got to get the computer woken up here. No. It's been so long, I need to log back in. All right, here we go. All right. So, here's one for you to try. It's similar in the fact it gives you success numbers of two different groups. In this case, it's American teens versus Japanese teens, whether they what rate they like anime. The only difference here is instead of giving you the percents, they actually gave you the success numbers. So you have the success numbers. In order to get the percents, you can just divide 72 by 325 and 75 divide by 268. But basically, you can read this problem and you can try it. The next video, I'll attach an extra video that has the solution to this, but I'd recommend that you try this on your own and see if you can come up with the conclusion. Basically, even though there's going to be some difference in the samples as to Americans versus Japanese liking anime, is this difference indicative that the populations actually like anime at a different rate? I think it's somewhat easy to see from the numbers that the Japanese sample came out higher than the American sample. But this may or may not be evidence that the two populations actually like it at a different rate. So see if you can determine this. Go through the 4 steps. And the next video that I will add on to this, I will show the solution to this and you can see how you did.